Back 1105, Chapter 6, Section 2. This deals with one-to-one functions, which are really inverse functions. A couple of definitions first. Definition of one-to-one means that all the x's and all the y's cannot be repeated. Remember, your definition of a function is that only the x's can't be repeated. Now, a one-to-one function is where the x's and the y's both can't be repeated. Horizontal line test is where we draw a horizontal line or an infinite amount of horizontal lines. If they only intersect one point on the graph, it's considered to be one-to-one. As an example, look at these. Okay, this particular mapping diagram is a function because none of the x's are repeated. It is one-to-one because none of the y's are repeated. However, this function, this particular relation is a function because all the x's are only used once, but it is not one-to-one because these two x's have the same y, these three have the same y. So relation can be a function or not, just by looking to see if the x's are repeated. From there, you can look to see or test to see if it's one-to-one. Just like this example problem here. If you look at this one here, we can see that it is a function because all the x's are only used once, but it's not one-to-one because this x and this x have the same y. We come down here, we look at our x's, they're all different, so it is a function. We look at our y's, they're all different, so it is one-to-one. Horizontal line test, just like I got through explaining to you, is where you draw a horizontal line. If it intersects more than one point, the function is not one-to-one. So the first test is to make sure that it's a function. X's can't be repeated. Or vertical line test where all vertical lines only intersect one point. Next test is to see if it's one-to-one. See if the y's are repeated. If they're repeated, not one-to-one, but still a function. If they're not repeated, it is a function and one-to-one. Some good examples are here. Okay. All right, first of all, if we did a vertical line test with this graph, we can see that it's a function. Once we do the horizontal line test, it intersects more than one point, so it's not one-to-one. And incidentally, that's the x-squared graph. Here's the x-cubed graph. We do our vertical lines, we can see that they intersect only one point, so it is a function. If we do our horizontal lines, we can see they're also intersecting one point, so it's a one-to-one function. Come back here. The notation for inverse functions is just by putting this little -1 up there. So it's considered f of -1, the inverse of f of x. Okay. Definition of an inverse function is where the x's and the y's switch places in ordered pairs. So if my function is x comma y, my inverse will be y comma x. Here is a good example of what they mean by inverse. If you look at this graph here, we have the points -2, -1, -1, 0, 2, 1. There's the function f of x. If we want the inverse, this 2, 1 will become 1, 2. This -1, 0 will become 0, 1, -1. This -2, -1 will become -1, -2. Thus, the pink line is the inverse of this function. Inverse functions are important because they give us exact symmetry of what we want. If you look at this shape here, if you were to rotate this 360 degrees, you would have, a glass or whatever, but you would have a perfect symmetrical shape. One of the ways that we verify that two functions are inverses of each other is drawn back from what we did in the last section. So what we're going to do, we have this g of x, which is x cubed, g to the -1 of x, which is cube root of x. So we're going to prove that these two are inverse functions. So what we do is we take the g of negative 1 of x and stick it into the x here. So we have g of negative 1 of x, which is cube root of x to the third power, which is really x to the 1/3 power to the third power. That's the product rule where we multiply. So it gives us x to the 3/3 power, which is x. Then we do g of negative 1 of g of x, which is cube root of x cubed, same mathematical reasoning, x cubed raised to the 1/3 power. These multiply, give me x 3/3, which gives me x. So anytime I stick one function into another and then reverse it, and I get 1x, 1x, it's mathematical proof that the two functions are inverses of each other. Meaning that if this ordered pair were xy, this ordered pair would be yx. Same thing with the next example. We have f of x equals 2x plus 3, f of negative 1 of x, 1/2 x minus 3. So we're going to take this f of negative 1x, stick it in for x here, see what we get. Then we're going to take the 2x plus 3, stick it in here, and see what we get. Here's the f of negative 1 of x, which basically 2 times 1/2 is 1. So now we get x minus 3 plus 3, so we get x. Here, we're taking f of x and putting it in, we're taking this and putting it in place of x. So we get 1/2 times 2x plus 3 minus 3. Well, plus 3 minus 3 cancels. 1/2 times 2x gives me x. So these two functions are inverses of each other. Go to the last example problem here. This is example 4 on page 429. Basically what we're doing is going to find the inverse for this function. First of all, we verified that it is a function. We verified that it's 1-to-1. And so now what we're going to do is find the inverse. So what we do first is we replace f of x with y. Then what I'm going to do is I'm going to switch I'm going to switch all the x's to y to x. So this y became an x, these x's became y. Then what I'm going to do is I'm going to solve back for y. So I'm going to multiply this y minus 1 over, distribute the x, and then I'm going to bring my y terms together. So I'm going to add this x over, but I'm going to subtract this 2y over. Then I'm going to factor out this y. I get y times y minus 2 equals x plus 1. Divide back by x minus 2. So now I get y equals x plus 1 over x minus 2, which is the inverse. So this f of negative 1 of x, x plus 1 over x minus 2, is the inverse of f of x equals 2x plus 1 over x minus 1. That means the ordered pairs here, per se, will be x comma y. The ordered pairs here will be y comma x.